Hello everyone, we will present our work, Merger, a divide and conquer approach to large-scale neural visual geometry. Structure from motion is a classic problem in computer vision and has been a popular research topic for over 40 years. Put simply, it asks the question, given a set of input images, how can we process them in order to recover a 3D point cloud reconstruction of the scene represented by those images, as well as the camera poses of those images during the time of capture? Traditional structure from motion techniques such as ColMap are highly iterative and computationally intense. They involve multiple sequential stages such as feature extraction, image matching, camera pose estimation, 3D point triangulation, and bundle adjustment. Notably, these final three steps are typically repeated for each image in the input set while also being the most computationally intense, leading to a high runtime and memory costs. Modern SFM techniques take a different approach. Instead of using iterative handcrafted algorithms, a large transformer network is trained to infer camera poses and point cloud reconstructions directly from the input image set. We call these neurogeometric foundation models. This paradigm shift opens the door to fast feed-forward SFM, leaving behind the fine-tuning of traditional techniques for a highly accurate plug-and-play solution. But there is a problem. The transformer architecture of these models severely limits their scalability. By their nature, the memory and runtime costs of these models scale linearly and quadratically, respectively, as demonstrated by these three variants of this new paradigm. These are prohibitively high requirements for someone working with limited VRAM or datasets of thousands of images. Introducing Merger, a backbone agnostic framework to scale up feed-forward neurogeometric foundation models and solve these problems. Given a set of input images, we pass them into our sorting algorithm, which orders them into a video-like sequence, what we call a pseudo-video. Then we split the pseudo-video into multiple subsets using our splitting algorithm. Each image subset is independently processed by a geometric foundation model to produce local reconstructions and camera poses. This is followed by an alignment step to bring all local reconstructions into one global coordinate frame, then a bundle adjustment step which produces the final refined global reconstruction. At a high level, Merger is a divide and conquer approach. It divides large input image sets into smaller subsets, reconstructing them locally to mitigate the quadratic scaling of the transformer architecture, then merges them together to produce one unified result. We will now walk through each step in more detail. The first step is the image set splitting algorithm. It works by first constructing a fully connected graph where each image is a node and each edge weight is the similarity score between the two images it connects. It then finds the longest Hamiltonian path through the graph to construct our pseudo-video. Then it uses interleaved sampling to evenly distribute scene information before using an overlapping sliding window to finally create the subsets. The next step is the per-cluster processing. Each image subset is independently passed into a geometric foundation model to create one local reconstruction per subset. We then leverage the overlapping images between subsets to align local reconstructions using a confidence-weighted version of the Umeyama algorithm, which helps mitigate the effects of outliers and poor point predictions. Finally, we use light glue for feature matching over a graph structure of images to efficiently extract long feature tracks throughout the combined image set. These tracks are then used by our bundle adjustment algorithm to produce the final refined global reconstruction. The key benefit of Merger is how it reduces the complexity of modern geometric foundation models from O of n squared to O of n squared over k, where n is the number of images and k is the number of subsets. Merger is able to effectively reduce both the memory and runtime costs of geometric foundation models by a whole complexity class, taking memory consumption from linear to nearly constant and runtime from quadratic to linear. The computational benefits of Merger do not sacrifice the reconstruction quality. In fact, Merger demonstrates state-of-the-art performance on standard benchmarks. Merger is also able to maintain large-scale visual consistency in challenging datasets when compared to competitors such as Pylong. In conclusion, Merger provides a framework to scale up any neural geometric foundation model by leveraging the strengths of classical and learning-based approaches to visual geometry estimation. An honest limitation of Merger is that the splitting algorithm can struggle to discriminate between visually similar scenes, leading to incorrect image clustering, and weaker global alignment. Thank you for listening to our presentation. Please check out our webpage at the QR code or the link on this slide if you'd like to learn more about Merger.